do today. We are going to look at some properties of logarithms. And then we're going to use those properties so that we can solve logarithmic equations. That's all we're going to do today is work on solving equations. So let me have you look at this. Here's what we've kind of done so far. One thing I hope to accomplish last week is for you to look at the word logarithm, and without panicking, with confidence, you can say, I know what a logarithm is. It's not this complicated, awful thing that's only used for rocket science. It's actually very, very simple. Fill in the blank. A logarithm is what? It's an exponent. A logarithm is an exponent. That's all it is. So when I say, like log base 3 of 19 or something like that, that whole thing, it's just an exponent. And specifically, it's an exponent that goes with the base of 3. It's saying 3 raised to what power gives me 19. And whatever that question mark value is, that's what that is. So when somebody's asking you to evaluate a logarithm, you're finding an exponent is what you're doing. Okay? So hopefully we understand what a logarithm is. Now we want to look at basic properties of logarithms and then use them to solve equations. Okay? So here we go. There's a few properties here. The product rule and the quotient rule, we'll run through them really fast. You can see them in your textbook. But I'm more interested in the power rule and the change of base property because we're going to use those much more. And why are we doing all of this? Because once we understand these properties and we understand how to do a logarithm, we can solve an equation such as the one shown there. 3 to the x power equals 17. Think all the way back to chapter 2 when we were just doing solve equations, right? We solved linear equations and quadratic equations and cubic and square root equations and rational equations. And all these equations, we were always solve for x, solve for x, solve for x. But never in chapter 2, 3, or 4, or 5 did we ever solve for an equation where the variable we were looking for was up in the exponent. Why did we not do that in chapters 2 through 5? Because you can't do it if you don't know what a logarithm is. And that's what we're doing now. So if you take anything away from this chapter and these rules, it's like, why would I ever use a logarithm? I would use a logarithm to solve when the variable I'm trying to solve for is upstairs in the exponent. That's what we're doing. Okay, so here we go. See if you can fill in the blank really quick in your head. X cubed times x to the 6th times x to the 7th. You learned how to do this in 7th grade. X to the 16th, I heard. Who said that? Anybody with her? Yeah, we know that one, right? If you take something, x to whatever, and it's the same base, right? Same base, same base, same base. What's our rule? What do we do with our exponents? You add them. Yep. We just add the exponents. Well, this is what the product rule then for logarithms looks like. Because remember, logarithms are exponents. So if there's some property called the product rule for exponents, then that same property is going to hold true for logarithms because logarithms are exponents. So if you have the logarithm of some base, whatever it is, and it's the logarithm of a product, two numbers times each other, m times n, that's the exact same thing as writing them as their own individual exponent where the exponents are added together. So that little formula right there, and you'll see it in your book, that's what they call the product rule of logarithms. And it's a way to rewrite an equation or an expression if you need to. And again, I'm going to fly through these first two rules. We're not going to focus on them. Let's fill in the blank here. That's a division, by the way. X squared. How did you know it was going to be x squared? You subtract the exponents, right? It's called the quotient rule, or it's one of our properties of exponents. We subtracted the exponents. So the same thing holds true for logarithms. If you have the logarithm of a fraction, where it's a denominator and a numerator, some division, you can take those individual exponents and you can subtract the exponents. That's what we did in our exponent rule, right? Okay, here we go. This is going to be a little more useful for us now today. X to the 12th. Very good. That's the same as saying x cubed, x cubed, x cubed, x cubed, but instead of writing it 4 times, we just raise a power to a power, right? And a power to a power, our rule is multiply the exponents. That's a power rule. Okay, so again, the same holds true for logarithms. So take a look at this one. Log base b of m raised to the p power. So first we got to go back and we got to ask ourselves, if we have log base b of m, let's ignore the p for a second. Just log base b of m. A logarithm is what? Fill in the blank? It's an exponent. So if I take an exponent and I raise it to an exponent, namely p, what do I do when I take an exponent raised to an exponent? You multiply them. So if I have an exponent raised to an exponent, that's the same as just multiplying that exponent times that exponent. So if you want to think of it, the p-value just kind of moves down in front. Watch this. I spent a lot of time making this PowerPoint. Watch the p. It can just go down in front. See how I did that? Show you again since I'm so proud of this PowerPoint. Okay, watch the p. It's an exponent raised to an exponent. What can I do with that second exponent? I can move it down front and multiply it. I'm multiplying 2 exponents together. That's going to be very helpful as we get going here. Okay, last slide, and then we'll try a few examples. This is what we call the change of base property. You might recall a conversation from the other day where I said, how would we evaluate something like log base 3 of 17 in our calculator? Because our calculator only has a button for log base 10 and log base e. At which Katie said, well, my calculator has one that you can do log base 3. Does that mean her calculator is better than my calculator? Maybe. But there's a super fast shortcut that makes it so that we don't have to have that button on our calculator. And that's what we're going to talk about here. Okay, so this is a shortcut. Imagine if you had, let's say I wanted to solve for log base 3 of 17. First of all, do you agree that those two things are the same thing? This is in exponential form. This is in logarithmic form. They say the exact same thing. They're just written 2 different ways. Okay? So if I'm looking at this guy over here, and I'm like, gee, I wonder what log base 3 of 17 is. Unless I have Katie's calculator, I'm not sure what to do with that right now. Right? You can estimate, like it's going to be what? 3 squared is going to be too small, right? But 3 cubed is going to be too big. So the answer is going to be somewhere between 2 and 3 if we just estimate it. Okay? So what happens if I took, I'll just write it up here on the board. Yeah, maybe I'll do it on the PowerPoint here. What happens if I took this 3 to the x equals 17, and I wanted to solve that equation? I'm going to take the logarithm of both sides. So log 3 to the x equals log 17. You guys okay with that? Whatever I do to the left-hand side, I can do to the right-hand side. Now look at my left-hand side. Log of 3 to the x. Log of 3 is an exponent. X is an exponent. What can I do with that x? I can move it down front like I did with the p, right? So that's the same as saying x times log 3 equals log 17. And now one more step. How do I solve for x? Divide both sides by log 3. If I divide by log 3 and divide by log 3, cancel. So x would be equal to this, right? So on your calculator, go ahead and punch in log 17, see what it is. I get 1.23. You get that for the numerator? And then hit divided by log 3. My final answer is 2.5789. Everybody get that on their calculator? We said it was going to be somewhere between 2 and 3, so that makes sense, right? 2.5789. So all the way back to here, if I wanted to find out what is log base 317, if I just take log 17 divided by log 3, I have it. That's why I don't need the fancy button that Katie's calculator has, right? Because as long as you use change of base property, you can do it. So I can give you any logarithm. I could give you log base 7 of 912. You can't do that in your head. I hope not. But what would you punch into your calculator to figure out what it is? Log 912, enter, divided by log 7. I think it's 3.5025. Are you with me? Here's what you can't type in, and I talked about this last week. This is not the same as saying log 912 divided by 7. That's a different thing. Okay? Not the same. So that is not what we want to do. We want to rewrite this as log of 912 divided by log of 7. Okay, look at the PowerPoint really quick. I chose to use log, L-O-G, which we know is log base 10, correct? What happens if I would have chosen to do log base E, ln? So what happens instead of log here if I would have used ln and ln? And here would have been an ln, and here would have been an ln, and here's an ln, and here's an ln. Would it still have worked? Try typing in ln of 17 divided by ln of 3. See if you get the same thing that we did when we used log. ln of 17 divided by ln of 3, I get 2.5789. Same thing, right? So when I use that change of base property, it actually doesn't matter what logarithm I choose to use. I can choose any base that I want at all. What base am I going to choose to use? I'm either going to do base 10 or base E because those are the two buttons that I have on my calculator. Are we cool? All right. I'm going to give you guys, let's see if I have any more PowerPoint slides. No, I don't. I'm going to give you guys a worksheet, and we're just going to work on these as practice in class. If you want to work individually, you can. If you want to saddle up beside a partner, you can do that too. All we're doing here is solving equations. I'm not going to ask you to hand this in. This is going to be yours to keep for your notes. This is just practice. Now, very quickly, before you get started here, all of these are going to require logarithms except number 1. Now, if you wanted to solve number 1 using logarithms, you could. But I would like to see if you could solve number 1 as though you've never even heard of logarithms before. See if you can figure out what I'm getting at and why is that one solvable without logarithms, whereas number 2 and number 3 and 4 and whatnot are not going to be. Actually, yeah, the rest of them are not. See if you can figure that out, and when you think you got something, flag me or Oren down, and we'll see if you know what you're talking about. This worksheet is on Blackboard, by the way. I'm going to pull it up on my screen. It's called 6.6. 6.6 exponential and log equations. Anybody got number 1 yet? What'd you get? Very nice. Did you just do it in your head?
Yep.
Okay, not bad. Yeah? Could you explain to Noah or Connor, can you explain to everybody else why we don't need logarithms? Other than I just did it in my head?
Well, it's pretty easy. I mean, 2 to the 4th is 16, so if you can find out what x is equal to make the exponent 4.
There you go. Do you guys agree that 16 is the exact same thing as 2 to the 4th power? So cross out the 16 and rewrite it as 2 to the 4th power. Does it look easier to you now? Because now on both the left and the right hand side, don't you have a 2 as your base? So if 2 to some exponent is equal to 2 to some exponent, what do you think is going to be true about your two exponents? They're going to be equal to each other. And if you can figure that out, now a little 8th grade algebra and you have your answer, right? So the key there would be to recognize that this 16 could be rewritten if I erase the 16 and I write it as 2 to the 4th power. Now you should see that 3x minus 8 must be equal to 4. And now I could just quickly solve. What does x equal? 4. What happens if that 16, I'm going to put it back there. What happens if that 16 was a 17? Then what? Could you do it? I think you could only do it if you used logarithms, right? Because now your answer is going to come out to some awful decimal. The fact that it was a nice number like 16, which happens to be a power of 2, that's why it worked. If it was 17 or 15 or 19, it wouldn't work. Okay, I'll let you try the rest of them. And again, if you want to check any of your answers with me or Oren, flag us down.
That would cross out the E, I think. Yeah.
What'd you do?
I don't know.
So, yep. I think your 40 is still clogging things up.
Yeah.
So, don't go there yet. Can you get rid of the 40?
Yeah, you can.
Yeah. And then go for the ln. You've got the ln of 40e. You want the ln of e. Yeah.
It might make sense.
So now you got
Then I take the ln.
e to the 0.6x equals, what'd you get, 6 on the other side? Now you can apply your logarithm. Did you guys get an answer for that one? Yep, okay, you're good. So now you're at this spot where you're trying to solve for x. X is up in the exponent. You don't want it up in the exponent. How do you get an x that's upstairs to come down? You can only do it, remember my little PowerPoint where the P went down like that? You can only do that if you do logarithms, right? So I think you need to take the logarithm of both sides. So maybe either log base 10 or log base e. And if you did the logarithm of both sides, that 0.6x can come, just like the p on the PowerPoint, it can come down. And once you get it down on the main road there, and he's not up in the exponent anymore, then you just use algebra like normal to solve. See if you can come up with something.
No, he just said log.
Yep. Correct, because it's 40 times e to the 0.6x. So it's e to the... Good. So what are you going to do now? Yeah. A lot of you on number 2 have gotten to this point. A lot of you are right here on number 2. And you got there by doing just a little bit of simple algebra. You added 3 to both sides, right? Then you divided both sides by 40. So that's like, so far what you've done is the 8th grade algebra. Now the college algebra is coming in at this step, right? Why are we doing logarithms again? It's so we can solve for equations where the variable is up in the exponent. Isn't that exactly what we have here? We have a variable that's up in the exponent. We don't want him up in the exponent. We want him to do that cool little thing that my PowerPoint did so it can come down in the front, right? But we can only do that if what? That rule that I showed you on that PowerPoint, we called it the power rule of logarithms, right? I can't just move it because I want to move it. I can only move it if I have a logarithm, right? So what do I need to have out front here before I can move him? ln or log base 10. We can do either one. Which one is the clever, smart one to use here? ln, because what's going to happen eventually? I'm going to have the ln of e. And what is the ln of e? 1. Whereas if I use log base 10, then I just got to deal with a big ugly decimal. It would work. But why deal with big ugly decimals when we don't have to, right? So, if I go like this, if I say, you know what, I'm going to take the ln of the left side and the ln of the right side. Yes. Now I can do that little move that I did on the PowerPoint, right? Where can this guy go? Down front, because it's an exponent raised to an exponent, which we know can multiply. So now it's 0.6x times the ln of e equals the ln of 6. And what did we just say the ln of e was? 1. So 0.06x times 1 is just 0.6x, right? The ln of e just goes away because it's times 1. So 0.6x is equal to the ln of 6. And now I can go back to 8th grade. How do I solve this guy? Divide both sides by 0.6. And now I could either leave my answer like that. This would be an exact answer. Or I could punch it into my calculator, which will give me a decimal approximation. Right? Either way is fine. Here's what I ended up getting for that one. I think it is equal to approximately 2.99. Did anybody get that when they punched it in their calculator? Yeah. So what's the key again? I feel like I'm repeating myself. The key is the x was up in the exponent, and the only way I can get it down is to use logarithms. And once I use logarithms, I can pull off that cool power rule. And once I pull off the power rule, now I'm just back to simple algebra again. Just solve for x. Okay. I can tell you that number 3 is a huge pain in the butt. So if you want, try 4. Try 4, 5, 4 and 5 first and come back to number 3. Number 3 is awful. But if you've already got an answer for 3, I'll come check it out for you. So don't overthink it now. That's
Would you distribute it?
not distribute.
Or you divide it?
No. So what you're looking at is you're looking at an equation that is in logarithmic form.
Yeah.
Can you make it into exponential form? That's what we practice.
Go back, like, to bring it back over?
So identify your base, identify your exponent, and identify your number. This is when we practice. Remember, I put up a left and right hand side grid the other day in class, and you had to fill it in. If it was in exponential form, change it to log form. If it was in log form, change it to exponential form. There you go. Exactly. So what happens if this was given to you right here? Could you change it into that form? And if you can, then you're going to recognize it as a very easy equation to solve.
I'm probably going to.
When you guys are looking at 4a, is the variable that we're trying to solve for, is it up in the exponent? No, it's not. Because it's already in logarithmic form, right? So we don't have to apply logarithms to try to move it. It's already down where we need it. All you got to do is be clever enough to recognize that that's in logarithmic form, and we practiced it last week. I can switch it into his equivalent exponential form, and if you can do that, then you have a really easy equation to solve. But you got to be able to switch back and forth from logarithmic to exponential. Anybody get that one yet? 4a? Yeah, very nice. You guys get that one? 13. 13? Yep, good. 4a is good, yes. Your b is wrong, though. So what'd you do?
Did ln of 2 times 3.
Yeah, nope. So remember what ln means. Ln means ln of 2x. The ln of 2x, this is the same as this. It says e raised to what power gives me 2x. Okay? So it's not a multiplication. It's not something you can punch in your calculator right now, because you're not going to punch 2x in your calculator, right? So what you should do is try to get rid of that 3, first of all. Can you move him? Just divide both sides by
3.
Yep, perfect. So now what are you going to do with this? This is in logarithmic form. The variable we're trying to solve for is not upstairs, right? It's already down where we need them. All we got to do, it's actually the same as this one. All we got to do is you change this guy from log into exponential, and you did that correctly. 4 raised to the 2 gives us x plus 3. Do that exact same step, but do it on that.
Can we change it to log from here, or do we keep it?
Well, it is in log, remember? ln is log base e. So back up on 4a, you had log base 4, right?
Yeah.
So you went 4, do your little circle thing. You had this. Back on 4a, you had log base 4 x plus 3 equals 2. And you said, here's my base. The 4 raised to the 2 gives me that. And you wrote this. Right? Do the same thing here. The base raised to the exponent gives me that number. The base, what is this equal to, 4?
Yeah.
The base, same thing. It used to be 4. In this one, it's e. E raised to that power gives me that number. And if you rewrite it, you're good to go. Perfect. Now solve for x. What are you how do you solve for x? Divide both sides by 2. Yep. So you got e to the 4th divided by 2. Now you can leave it like that, or you can write down the decimal approximation. Did you get about 27.3? Yep. There. Good. Very nice. Yep. Good. Where did I put it? I divided both sides by 3. So, at the very beginning. So, this is just 3 times this.
Yeah.
So it's 3 times ln of 2x. ln of 2x is some value, right?
Yeah.
If I just divide both sides by 3, wouldn't the 3 cancel and I'd have a 4 on the other side? So, like, try to do your simple kind of 8th grade algebra type stuff first before you get yourself into logarithm mode. Simplify with simple algebra first. So here's what my 4a looked like. I got 13. That one, if you recognized how to change it from log form into exponential form, that's what I did on that first line. After that, it became a super easy problem to solve. But you have to be able to switch from log form to exponential form, and sometimes from exponential form back to log form.
So we all did
We didn't do 3 yet in class,
no,
but
I
yep.
meant 2, she said.
Yeah, 2 is, I had it up there just a second ago. Here we go. I got about 2.99. Or you could have left it as this fraction right here.
Okay, yeah, I see what you're saying.
Anybody get number 5 yet? What'd you get?
0.081.
Mm-hmm. 12.77. Good. Good. Did you use... so the only thing to do here is when you... you divided both sides by 6. What is 17 divided by 6?
2.83 repeating.
Okay.
Well, the
So
3 is repeating.
the 3 is repeating. Right. So it works out fine. So, and you already know this. In certain exponential growth, logarithmic growth, stuff like that, be very careful about your rounding. Because 2.83 is different than 2.8333333, right? So if you want to be more precise.
I think I did use the calculator. I just wrote this down.
Gotcha. Yep. Yep. So instead of writing a decimal, I wrote 17 divided by 6, which again is more precise.
Yeah.
Yep. Yep. It'll make a difference when you get to money over 40 years, that kind of stuff. Yeah.
We're on the right track.
Check your other ones. Did you finish?
No.
See if you can do 3. Did I scare you off when I told you how bad it was going to be? Mm-hmm. So log. So keep in mind here now that the 5, it's 5 is the base, x minus 2 is the,
Okay.
right? So when you do log, it's the 5 is not up there.
The 5 is actually down.
Right.
Okay.
So it'd be log of that divided by, equal to log of 4, and then the exponent is 2x plus 3. And the reason you would ever want to do that is because you don't want that x upstairs. You want him down, right?
Right.
You don't want this x upstairs. You want him down. And now that we have this logarithm, remember this log 5, it's an exponent, raised to an exponent. And what do? Exponents to exponents? We multiply. So we can do that move that I did on the PowerPoint, right? So now I have x minus 2.
So my log would just move.
And now I just have log 5. That's all I have.
So it would just move down here.
Correct. Yep. And be careful now. This is different than this. I need to take the whole darn thing times log of 5. Correct. Yeah, you can't miss your parentheses. Same with things with that 2x plus 3. Can't miss your parentheses. Now it's a exercise in distributive property, gathering like terms. You got 2 x's right now, and you need to get down to 1 x. That's where I said it gets a little bit painful. Yep. So you got x minus 2 log 5, 2x plus 3 times log 4. Yep. So solve for x, right? Now don't let the log 5 and log 4 confuse you. All they are is ugly decimals. They're just numbers. So you can treat them algebraically like the ugly decimal that they are, but you can just leave it as log 5. So if this was some ugly decimal times x minus 2, what would you do with it?
Divide it.
Not divide it. Well, you could. Yeah, you could divide right away, but you're still going to have x minus 2. It depends on the order of operations, but yeah, I would distribute it. Distribute it
to the x.
And distribute it. Gather my like terms. Get x all together, factor out the x, and solve. I know, there's a lot of algebra going on there. Okay, I'd like you to try to finish this. I'm gonna post the solutions document on Blackboard so that you can just look at it. So if you're just gonna look at it and copy it down for the sake of finishing it, so be it. Or you can actually try to work through it on your own, see what you get, and then go back and check your answers. However you decide to do that is fine. But when you come back on Friday, we're going to actually start doing kind of like more application problems and models that involve logarithmic growth and exponential growth. So it'll be a little more fun than today. All right. See you on Friday.
I'll let Jody know you're coming. She won't worry about you.